I think today is week 6, okay, week 6 lecture. Okay, so before we proceed, as usual, I need to do some sound check. So can you all hear me before I proceed to make an announcement regarding to our test? Shinny, can you hear me? Yes, thank you. Okay, thanks, Alvin. Okay, so before we proceed to our lecture, okay, just a reminder here. Okay, so today is week 6. Okay, next week is week 7. So I already told you. So later in week 7, we have a test for this module. Okay, and for your information, the test will be conducted physically face to face in our campus. Okay, so the coverage will cover from our lecture 1 until lecture 5 and including lecture 5 and tutorial 4, okay? Lecture 5. Okay, lecture 5 is actually the heat integration, okay? Design the heat exchanger network, okay? So basically for our test, okay, it will cover from lecture 1 until lecture 5, okay? In our test, we only have 2 questions and no equation will be provided for our test. Okay, so be careful. So make sure you do all the revision. Okay, you read all the lecture notes and also try to solve all the tutorial question. Okay, so remember for our test, we only have 2 questions. Okay, okay. So the test will be conducted physically by using our lecture time slot. Meaning that next week we don't have any lecture, but for next week you need to go to campus, okay? And we will use the lecture time slot to do our test. And the test will start at 2:30 and at 3:30. You all will be given 1 hour to answer 2 questions only. Okay, for the test, it will be conducted, okay, in the, I think this one is classroom, D809. Okay, so actually I already updated, okay, the announcement in your e-learning portal. So later you can try to open out your e-learning portal my times so that you can, okay, know what is the coverage and also time and venue for your test. Okay, so remember for next Tuesday, okay, make sure you go to campus, okay, because next week, next Tuesday, we will conduct, okay, we will use the lecture time slot to conduct our test. Okay, so far, any question regarding to the test before we proceed to our lecture today? Okay, I assume no question. Then, okay, we will directly proceed to our lecture today. Okay, today we will proceed to our chapter 7. Okay, in our last week lecture and tutorial, we already learned how to try to design the thickness of the pressure vessel, okay, to make sure it is strong enough to support the internal pressure. So remember what is internal pressure? Internal pressure, that means the operating pressure. Especially if let's say you want to operate the process in the pressure vessel by using the operating pressure, which is higher than atmospheric pressure, then in that case, you need to make sure the thickness of the shell is actually thick enough, strong enough to support, okay, the operating pressure without rupture, okay? And also last week, we also learned how to try to select the suitable closure and also the head in order to cover our pressure vessel, okay? So basically, this is what we already learned in our previous lecture and tutorial. So in our today lecture, chapter 7, yes, we will proceed with our mechanical design. But in our today lecture, we will try to learn how to try to calculate or identify the thickness for the shell of our pressure vessel to make sure it is strong enough to support the external pressure. Okay, external pressure. Last week we deal with internal pressure. Today we will deal with external pressure. So in our today lecture, first I will try to share with you, okay, several common and different design that we normally apply in the industry in order to design the pressure vessel to make sure it is strong enough to support the external pressure. And also after that, okay, I will try to show you the equation that we normally apply to calculate, okay, and identify the thickness for the shell of our pressure vessel to make sure they are strong enough to support the external pressure. So once we already cover all the external pressure design and calculation, then we will proceed to the combined loading. Okay, for the combined loading, okay, this one I will explain later. Okay, okay, so far any question? So basically, these are the three subtopics that we are going to cover in our today lecture. Okay, so now we proceed. Okay, give me 20 seconds. I adjust something. Okay, so we proceed. Okay, so now today we will only focus to the external pressure. Okay, before we proceed, I think it's good I try to explain a bit what is external pressure. Okay, you try to imagine now you are given a pressure vessel. Okay, last week we only cover or we only deal with the pressure inside the pressure vessel. So that's why the pressure we cover last week is also known as internal pressure. For external pressure, that means now we need to make sure the the wall or the shell of our pressure vessel is actually strong enough and thick enough to support, okay, the pressure outside the pressure vessel. And the pressure outside the pressure vessel is known as external pressure. Okay, so you try to imagine now there is a pressure outside the pressure vessel here. So common sense, okay, pressure is actually considered as a stress. Okay, so if let's say now the outer surface of the pressure vessel here is subjected to the pressure, subjected to a stress. So what will happen is the stress here, it can also consider as a type of force which will try to push the outer surface of the pressure vessel here. So you try to imagine. So if let's say now the shell of the pressure vessel here is not thick enough, not strong enough to support the force due to the pressure outside the pressure vessel here, what will happen is if let's say the force outside the pressure vessel here is bigger or larger than the pressure inside the pressure vessel here, what will happen is, okay, let's say this is your pressure vessel. What will happen is the stress or the force, they will try to push the outer surface of the pressure vessel here. And once the force here is bigger than the pressure or force inside the pressure vessel here, you are resulting in the deformation we call buckling. Okay, so now this is the outer surface of the pressure vessel. Here is the force, here is the stress. If let's say now the force or stress of the pressure outside the pressure vessel is larger than the pressure or force inside the pressure vessel here, then what will happen is the force here, initially the surface of the wall here is flat. But if let's say the external pressure outside the pressure vessel is larger than the inside here, what will happen is the force here, they will try to uh, push the outer surface here and make the outer surface or the shell or the wall of the pressure vessel here become like this. Why? Because there is a force, okay, outside the pressure vessel. They try to push the outer surface of the wall or the shell of the pressure vessel. Okay, and initially the surface is flat. Okay, due to the force here, then what will happen is now, okay, it will result, okay, it cause the deformation here, and this deformation is known as buckling. Okay, so you can try to imagine when there are a lot of forces outside the outer surface, okay, and some more the pressure or the forces outside the pressure vessel is bigger than the internal pressure or force that can be found inside the pressure vessel here, what will happen is all the forces here, they will try to push the outer surface, okay, or the wall, okay, or the shell of the pressure vessel here. And the force here can be considered as a type of compressive force, or we call compression, okay? And this compressive force or compression, they will try to push the outer surface, resulting in deformation. And this kind of deformation is known as buckling, okay? Okay, so this is what we call external pressure. So that's why when we design the thickness, okay, for the shell of our pressure vessel, not only we need to consider the internal pressure, but sometimes we also need to consider the external pressure to make sure the pressure vessel here can be safely operated. Okay. Okay, so far, any question regarding to the external pressure before I proceed to discuss? Okay, so if there's no question, then now I want to proceed. Okay, you may ask, sir, how do I know when I design the pressure vessel, I need to consider the internal pressure or external pressure? Ah, so in this case, you need to try to compare the pressure inside the pressure vessel and also a pressure outside the pressure vessel. Okay, so there are three different scenarios or three different cases we need to consider the external pressure. For example, now you are handling a pressure vessel. Okay, now the pressure outside the pressure vessel is, let's say, 1 atm or atmospheric pressure, okay, or atmospheric pressure. Now the pressure outside the pressure vessel is atmospheric pressure 1 atm. But due to the process here, okay, I need to operate the process here at the pressure, let's say, lower than 1 atm. If let's say the operating pressure inside the pressure vessel here is lower than the atmospheric pressure, lower than 1 atm, let's say 0.4 or 0.5 atm. So in this case, the pressure vessel here is considered operated under vacuum. Since the operating pressure inside the pressure vessel is lower than the pressure outside the pressure vessel here. So meaning that later the forces outside the pressure vessel is actually much stronger compared to the pressure of forces can be found inside the pressure vessel here. So in this case, we need to make sure the wall or the shell of the the pressure vessel is actually thick enough, strong enough to support the external pressure here. So in this case, we need to design the thickness, the shell here based on the external pressure calculation. This is the first scenario. Okay. Ah. Okay. The second scenario is, okay, if let's say now similar, I try to carry out and operate the pressure vessel here under vacuum. Under vacuum, that means the operating pressure inside the pressure vessel is lower than 1 atm. Okay, so that's why it's also known as operated under vacuum. If let's say the operating pressure is lower than 1 atm, and some more the pressure outside the pressure vessel here, okay, due to some of the cases, the out the external pressure here is actually higher than atmospheric pressure, higher than 1 atm. So in this case, we also need to design the shell of the pressure vessel based on the external pressure calculation. Why? Because if let's say we compare, okay, the pressure inside and outside the pressure vessel here, the pressure outside the pressure vessel is actually still higher than the operating pressure can be found inside the pressure vessel here. So in this case, this one is also considered external pressure calculation. This is the second scenario. We need to try to design the thickness based on the external pressure calculation. Okay. 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 Third scenario. Now, I try to operate a process by using a pressure vessel. Let's say a reactor. Okay. But okay, if let's say you remember in your mass and energy balance, okay, actually we can base on the energy balance to determine, okay, either the process is exothermic or endothermic, okay, and based on the exothermic or endothermic, we can, okay, decide whether we want to apply the heating process or cooling process in, okay, for the chemical reaction here. Okay, if let's say now the process here is an exothermic process. Exothermic process, that means a lot of heat energy will be released out. Okay, so in that case, we need to apply cooling process to cool down, control the temperature of the process and absorb the energy that released out. So in that case, what we will do is, in order to carry out the cooling process, we will try to install another layer we call jacket outside the pressure vessel or reactor here. And later the water, cooling water will flow through the gap between the pressure vessel and the jacket here in order to absorb the heat energy that released out from the reactor or pressure vessel here. But okay, don't forget, when the water flew through the gap between the jacket and the pressure vessel, okay, you will make the pressure, okay, that can be found in the gap here is actually higher than the pressure, the operating pressure inside the pressure vessel here. So in that case, we also need to make sure the wall or the thickness of the pressure vessel is actually designed based on the pressure that can be found inside the jacket here. Even though the pressure outside the jacket, outside the pressure vessel is 1 atm. But now the surface, the outer surface of the pressure vessel of the pressure vessel here is actually subjected to the pressure of the cooling water that flow through in the gap inside the jacket here. So that's why in this case, this one is considered as third scenario. Then we also need to try to design the thickness based on the external pressure. Okay. So these are the three common scenarios that normally we need to apply the external pressure to calculate the thickness, okay, of the pressure vessel that we are going to install. Okay. Okay, so far any question with my explanation here? So make sure later, because in future you are going to design the pressure vessel, no one will try to uh, tell you, okay, you are going to use the internal or external pressure calculation. You need to design, you need to decide yourself. Okay, how to decide? How to decide? You need to consider the pressure inside and outside the pressure vessel. Okay, and this is how we try to identify whether it is an internal or external pressure. Okay, especially later in let's say in your assignment or maybe in your final year design project or maybe in your final exam, if let's say they ask you to design the thickness, okay, without telling you to apply the internal or external pressure calculation, then you need to identify yourself. Okay. Okay, so far any question before we proceed? Okay, so if let's say no, then we proceed. Okay, this is what we call buckling. You see, okay, here is the outer surface of the pressure vessel. Okay, you see, now because the thickness, okay, the thickness of the pressure vessel here is not thick enough. So, and the pressure of compressive force outside the vessel is bigger, then you are trying to compress the outer surface and try to deform the pressure vessel here. And this kind of this deformation is known as buckling. You see, this one is also buckling. Okay. So that's why it's very important to make sure you design the thickness, the pressure vessel properly and correctly to make sure it can be safely operated. Okay, you see, okay, this one I share with you a video. This is how the buckling, okay, occur. Okay. Wait, you see, this is what we call buckling. Okay. the deformation is actually sudden and irreversible. So that's why it's very dangerous. Uh, okay, you need to try to imagine. Okay, this one is we call buckling. Now because the pressure vessel here is empty one, so that's why it just deform like this, we call buckling. But now you try to imagine, now you are actually running a chemical process, okay, or process inside the pressure vessel here. And there are some of the, let's say the gas and liquid mixture can be found inside the pressure vessel. If let's say suddenly, okay, suddenly buckling, okay, happen and occur, okay, what will happen is, okay, because if let's say if let's say suddenly, okay, there are some of the gas and liquid mixture can be found inside a pressure vessel, and some more suddenly buckling, then what will happen is all this gas and liquid mixture, okay, it might suddenly, okay, release out. Okay, let's say if let's say the closure or the head here is also not strong enough, then what will happen is maybe here will also rupture and the gas and liquid mixture can release out from the pressure vessel. So in that case, it can, okay, it can cause what we call the fire, toxic release, and also explosion as well. So that's why the design of the thickness is very important. Yeah, Edmund. Okay, this is a very good question. So that's why if let's say you want to try to design a submarine, then you also need to make sure the wall, okay, of the submarine is actually strong enough to support or tahan, okay, the water pressure. Okay. Okay. So okay, now, okay, beside the thickness, actually there are a lot of other properties, okay, of the pressure vessel. You will also influence the stability, okay, or we call the rigidity of the pressure vessel here in order to withstand, okay, or support the external pressure. One of the important property is known as elasticity, and the elasticity is actually depends, okay, the first reason, okay, the first factor that will determine or influence the elasticity is the material that we are going to select and use to construct the pressure vessel here. So common sense, okay, you learn the material property, okay, in your first or second year already. So okay, different materials, they have different elasticity. And some more, if let's say you compare the similar material at different, let's say, operating temperature, the temperature that it will also decide and also influence the elasticity of the similar material. So that's why, okay, not only the thickness is important, but when we try to design the shelf, okay, of our pressure vessel to withstand the external pressure, not only a thickness, the the elasticity is also one of the important properties that normally we need to consider, okay, to ensure the pressure vessel that we are going to fabricate, okay, is actually strong enough in order to support or withstand the external pressure. Okay. Okay, we do some revision. What is elasticity? Okay, elasticity is actually can be considered as the ability, okay, of a material, okay, in order to withstand, okay, or to resist the compressive force that applied or exerted by the external pressure. Okay, and you try to imagine now this one is your pressure vessel. And now, okay, here is your operating pressure. Let's say it's 0.5 atm. And now the external pressure is 1 atm. So the external pressure is actually bigger than the operating pressure. So now what will happen is now the pressure, the force, the compressive force outside the pressure vessel here is actually bigger than the force or pressure that can be found inside the pressure vessel here. So in this case, they will try to compress the outer surface of the pressure vessel here. They will try to compress and try to deform or change the shape of the pressure vessel here. So if let's say now the thickness here is actually thick enough, and some more the elasticity of the pressure vessel here, the material that we use to fabricate the pressure vessel here is actually strong enough, what will happen is the elasticity, okay, of the material that we use to fabricate the pressure vessel here, it will try to withstand, okay, to try to counterbalance, okay, or how what we say is try to track off, okay, the compressive force, okay, that applied by the external pressure here. So meaning that this one is the compressive force, and some more the elasticity here, they will try to maintain the shape of the pressure vessel here, and it will try to counterbalance or try to cancel off the compressive force here in order to make sure the pressure vessel here can assist and continue to carry out the process here without changing the shape of the pressure vessel here. This is the importance of the elasticity of the material of the pressure vessel that we are going to use to operate the pressure here in order to make sure it can be operated safely. So in other words that, okay, in other words that, okay, not only the thickness, okay, you can also make sure, you can make sure our pressure vessel, okay, can be safely operated. But the thickness here, you also need to, okay, work together with the elasticity of the material that we use for the pressure vessel here to make sure, okay, they are actually strong enough to support the pressure vessel here without changing its shape. Okay, and the elasticity here is actually an indicator that actually can indicate or represent the stiffness or rigidity of the pressure vessel here. So common sense, the higher the elasticity of the material or the pressure vessel here, the higher is the stiffness, higher is the rigidity of the pressure vessel here. So in this case, okay, the higher, okay, is the stiffness, okay, the higher, okay, the stronger is the pressure vessel here in order to withstand the external pressure outside the pressure vessel here. Okay, so in this case, it can avoid buckling. Okay, to avoid buckling. So if let's say the thickness, okay, of the pressure vessel here is not strong enough, not thick enough, okay, or the elasticity of the pressure vessel here is lower than the minimum value, then what will happen is, okay, it causes buckling, okay, and buckling is also known as elastic buckling, okay. So that means later what will happen is the outer surface, the shape of the outer surface of the pressure vessel here will deform or change. So that's why buckling is also known as elastic buckling. Okay. Okay. So, okay, here are the variables that actually we need to consider when we try to design our pressure vessel for external pressure. Okay, so I repeat, if let's say we want to make sure we want to design a pressure vessel and make sure it can be safely operated to withstand, okay, the external pressure, here are the four variables that we need to always consider in our design. Okay, the first one is the thickness. Okay, of course, the bigger the thickness, the more stable is the pressure vessel. Okay, this one I explained already just now. Beside that, it also depends on the properties of the material that we are going to use and select for the pressure vessel. Among the properties, okay, as I told you, the elasticity, okay, is the most important property. Okay, of course, the higher the elasticity, the more rigid, okay, is the pressure vessel that we can fabricate. Okay, so beside that, okay, diameter and also the length of the pressure vessel, we also need to consider. Why? Because the diameter and the length of the pressure vessel, they can also influence uh, the strength, okay, or the rigidity of the pressure vessel that we are going to design to withstand the external pressure. And normally, the larger the diameter of the pressure vessel, the less stable is the pressure vessel. Okay? In other words, if let's say we want to increase the stability of the pressure vessel here, we need to try to minimize the diameter, okay, of the pressure vessel. But of course, we also need to consider the amount of uh, the content, the process content, or the mixture that we are going to handle also to make sure the volume is actually sufficient. And also, we need to consider the length, okay, because, okay, the longer the length of the pressure vessel, the less stable is the pressure vessel. These are the four variables that we need to consider in our design, okay, in order to make sure the pressure vessel that we are going to design is actually stable to withstand the external pressure. So that's why later when we try to apply the equation to calculate the thickness, okay, of the for the pressure vessel here, okay, normally we will try to include the diameter, length, thickness, and also the elasticity in our calculation in the equation that we are going to use in order to determine the most suitable thickness for our pressure vessel here. Okay. Uh, and later I will show you the equation that we are going to use to calculate the thickness for the pressure vessel here in order to withstand the external pressure. And when the scientist or engineer that derive the equation, actually they already consider all the variables that I tried to explain just now. And some more in their derivation, they also try to include the factor of safety in the derivation, okay, before they get the final equation that we are going to use. And the reason why they include the factor of safety in the equation derivation, because they want to make sure later the thickness that you are going to design by using the equation that they recommend to you is actually safe enough, okay, for the design here. Okay. Okay, so far any question before we proceed? Okay. Okay, so now we proceed. Okay, so now, so in order to make sure the pressure vessel, okay, can be safely operated and some more can withstand the external pressure, the most simple method is we try to increase the thickness of the pressure vessel to make sure the thickness is actually thick enough, strong enough in order to withstand the external pressure. This is the first method, and this is the most common method. Ah, so means that if let's say you want to increase the thickness, you want to design the thickness of the shell, okay, for the pressure vessel to withstand the external pressure, okay, then we need to apply the relevant equation in order to get the thickness. The equation I will show you later. Okay. Okay, before we proceed, okay, I just want to highlight when we design the thickness, right? When we design the thickness for the pressure vessel to withstand the external pressure, we need to consider the effective length of the pressure vessel. Okay, what is effective length? Okay, you see, okay, here is actually, okay, from here until here, this one is known as the length of our shell. That means here is actually the height or the length of our pressure vessel. Here is actually our head or our closure. Here is our head, here is our closure. Okay? Okay. So you see, starting from here until the top part of the head here, this one is actually considered as the head or the height of our head. This one is also considered as the height of our head, the height of our closure. Okay. So, okay, here is the height of our closure. Here is the height of our head. Okay. Okay. Based on the height here, we need to calculate what is the amount of the 1/3 of the height of the head, of the height of the closure here. Similar, here we need to calculate 1/3 of the height of the closure here. Okay. And then after that, you need to add out the length of the shaft here, the length of the pressure vessel here, with the 1/3 value here, and also the 1/3 value here. Then the total answer, total length, is known as effective length. And when we design the thickness for the pressure vessel to withstand the external pressure, we need to consider the effective length. So meaning that we cannot just consider the length of the shaft here. We need to consider from here until here. We need to include another 1/3 of the height of our closure here, and also 1/3 of the height of our closure here. And this part, the total length here, is known as effective length. Okay? This is the method how we design the thickness. Okay? And normally the design of the thickness, we need to consider the effective length. Okay? Okay? Okay, this is the first method, how we try to design a pressure vessel to make sure it's strong enough to withstand the external pressure. But in case, if let's say after you try to calculate the thickness is actually very thick, okay? Because common sense, when you increase the thickness, what will happen is you will significantly increase the cost, okay? So if let's say, okay, suddenly you notice the thickness is too thick already, and you don't want to proceed with the thickness that you calculate based on the equation, then the alternative is we can try to install stiffening ring, or it is also known as stiffener, in order to increase the strength of the shaft of the pressure vessel here in order to withstand the external pressure. Okay? Okay. So I try to explain now what is stiffening ring, what is stiffener. Okay, you try to imagine. Now you have a horizontal cylindrical pressure vessel. Okay, this one. Now you want to withstand the external pressure, and you want to install the stiffener or stiffening ring. Then what will happen is later you will try to install a ring outside the on the outer surface of the pressure vessel here in order to provide, okay, the extra stress or strength in order to assist, okay, the pressure vessel here to withstand the external pressure. And this one, okay, then this one, okay, the ring that we install here is known as stiffening ring or stiffener. And the installation of the stiffener or stiffening ring here, okay, they can actually try to provide, okay, you can imagine it's actually provide, okay, the external support, okay, in order to assist the pressure vessel here to withstand the external pressure. Okay, depends on your design. Okay, okay, you can decide how many number, okay, how many ring okay, that you are going to install on the outer surface of the pressure vessel to make sure it's strong enough to withstand the external pressure. Okay. Ah, okay, this is the alternative how we provide the external support, okay, in order to strengthen, okay, to reinforce the outer surface of the pressure vessel here to make sure it's strong enough to withstand the external pressure. Okay, this is the example of the installation of the stiffening ring. You see this one? You see, the number of the ring that you are going to include, okay, depends on the strength that you want to provide lah, in order to withstand the external support. And the ring here, okay, there are two common different type of ring we can install, okay, in order to, okay, reinforce the outer surface. The first one is known as T-shaped ring. T-shaped ring is like this one. This one is the ring, the outer surface of the ring. This one, this part, you see this part is here. You see here is empty one. And right hand side here is also empty one. The shape is like T. So that's why the ring here is known as T-shaped ring. This one is known as L-shaped ring. Why? Because the ring is like this. This part is here. Here. And you see, here is the inner surface. Here is empty one. Here is empty one. The shape is like alphabet L. So that's why the ring here is known as L-shaped ring. Okay. So later we will also learn how to apply the equation, okay, to determine the suitable thickness for our pressure vessel. Okay, if let's say we want to install the stiffening ring to support our pressure vessel. Okay, we will cover the calculation later. Okay, beside that, okay, as I told you just now, okay, if let's say now the pressure vessel here, the outer surface, okay, we also install another layer of jacket. Okay, you try to imagine this one, okay, consider this one. This one you cannot see. Okay, never mind this one. This one. Okay, this one is your what we call the pressure vessel. It's the outer surface. Okay, now you want to try to install, you want to remove the heat energy that released out from the pressure vessel. Then in that case, the outer surface of the shell will be covered by another layer we call jacket. And then layer the cooling water will flow through between the gap, okay, the gap between the shell and also the jacket. And the gap, the thickness of the gap, okay, and also the size of the jacket, that one is actually depends on your design. So in this case, you see, now this one is the pressure vessel. Now here is the jacket. Later, okay, the cooling water will flow through the gap here. So in that case, if let's say the process inside the pressure vessel is not operated under vacuum, but there is a layer of jacket here. So in that case, later when you try to consider the external pressure, okay, you just only consider this part. Why? Because you need to make sure the thickness of the pressure vessel here is actually thick enough in order to withstand the external pressure that can be found inside the gap inside the jacket here. Okay, and later the length that you are going to use is here. Okay. Okay, this one you only have one layer. But if let's say in your design you install two different layer of jacket, and some more the jacket here, they are not connected to each other. So in that case, here there is an external pressure, and also external pressure can also be found here. So in that case, you need to consider the length here and also the length here to make sure the thickness here and here is actually strong enough. This is the example, okay, of the what we call the jacketed pressure vessel. This one is your pressure vessel. This one is the jacket, the brown color, this one. And actually there is a gap between the shell and also the jacket. And the water will flow through the inner surface to remove the heat energy. Okay, you see, this one is the shell. Oh, this one is the shell, and here is a jacket, and water will flow through the outer surface of the shell here. Okay. So beside that, there is another type of design that actually we can try to remove or supply the heat energy to the pressure vessel. Just now we try to remove the heat energy or supply the heat energy to the pressure vessel by using jacket. Okay, instead of using jacket, we can also try to install, okay, the what we call the half pipe in order to remove or supply the heat energy to the pressure vessel. And later the cooling water or hot water will flow through the gap inside the half pipe here in order to transfer the heat or absorb the heat from the pressure vessel. So meaning that just only the design, how we are going to try to transfer the hot water and cooling water to flow through the surface, outer surface of the pressure vessel is different. Okay, just now we use jacket, this one we use half pipe. This one you see example, this one is half pipe. Okay, you see the water is actually flowing inside the half pipe here, either to supply heat or absorb the heat from the pressure vessel. And normally when we design the half pipe here, we will try to design the length of the half pipe here properly and carefully. Okay, why? Because if possible, we want to try to minimize the external pressure that is that is exerted on the outer surface of the pressure vessel here. So in order that external pressure can be ignored. Okay. So even though when we try to design the half pipe here, we will try to design the length here carefully to make sure the external pressure that is going to exerted on the outer surface of the pressure vessel here can be ignored. Okay, even though the external pressure is small and can be ignored, but normally when we design, we still will consider the external pressure that can be found in the half pipe jacket here. Why? Due to a safety consideration. Okay, and if let's say you are using the half pipe jacket to supply or remove the heat energy, and some more you want to determine the thickness that you are going to design for the pressure vessel here to withstand the external pressure, then in that case you can refer to the standard. Okay, and inside standard actually they provide us the equation or the method how we can determine the thickness if let's say we are using half pipe jacket. Okay, so beside that, there is an alternative. Okay, we can try to support, okay, the outer surface or the shell of our pressure vessel. Okay, if let's say we want to install the jacket to remove or supply the heat energy to the content in the pressure vessel. Okay. Okay, so if let's say now you want to try to remove or supply the heat energy to a content inside the pressure vessel by using the jacket. Okay, if let's say this one is the jacket, outer surface of the jacket is here, outer surface of the shell is here. Okay, the common jacket is the water will flow through the gap in order to supply the energy or remove the energy. So in that case, we also need to make sure the thickness of the shell is actually strong enough to withstand the external pressure that can be found inside the gap here. But okay, according to some of the design, okay, that proposed by the scientists and also the engineer, okay, they noticed that, okay, actually we can also install the support which is known as stay root, okay, inside the gap between the jacket and also the pressure vessel in order to support the outer surface of the shell here to tahan or to withstand the external pressure that can be found inside the jacket here. Okay, I repeat. Okay, some of the engineer and scientists that propose and point out that, okay, instead of just increasing the thickness to withstand the external pressure inside the gap between the jacket and also the pressure vessel, we can also try to install the support, which is known as stay root, in order to strengthen the outer surface of the pressure vessel to make sure it's strong enough to withstand the external pressure in the jacket here. So for example, this one, okay, this one, okay, you see, this one is known as dimple jacket, okay, and dimple jacket is actually a form of the stay surface design. What is stay surface design? This one, we strengthen the outer surface of the pressure vessel by using the stay root. Okay, this one, this method alternative is known as stay surface, okay, method. And one of the example of the stay surface design is dimple jacket. They try to include the stay root in order to strengthen the outer surface, in order to make sure the outer surface is actually strong enough to withstand the external pressure. Okay. Okay, so far, any question before we proceed? Okay, so if let's say no question, then we proceed. Okay, just now we only consider one of the external pressure. Either the external pressure is actually come from the jacket or come from the environment. But in some of the processes, we need to consider multiple sources of external at the same time. For example, by taking the diagram here as an example, now you try to imagine, now the operating pressure here is lower than 1 atm. This one means that the process is operated under vacuum, okay, under vacuum. So in this case, we need to make sure the wall or the thickness of the shell here is strong enough to withstand the atmospheric pressure. And some more, now the pressure vessel here is layered by another layer of jacket. So in that case, we also need to consider the external pressure that can be found in the gap of the jacket here. So in this case, we have multiple sources of external pressure. So in this case, what you need to do is you need to try to consider all the external pressure here in order to make sure later the design of the pressure vessel here is actually strong enough to tahan, to withstand all this external pressure 1 and external pressure 2 here. And sometimes the calculation or design can become complicated, okay, compared to what I tried to explain just now. Why? Because now you need to consider multiple different sources of external pressure at the same time, okay? Okay, so now I want to show you the method how you are going to calculate the thickness for the pressure vessel to make sure it's strong enough to withstand the external pressure. Okay, if let's say now you want to increase the thickness, you want to try to make sure the pressure vessel is strong enough to withstand the external pressure, okay, by using its thickness, then you need to follow the method that I'm going to explain to you here. Okay, okay, first what we need to do is we need to assume a thickness for the shell of our pressure vessel. Okay, and based on the assumed thickness of the shell, you need to calculate the ratio here. The first one is the length ratio the outer diameter. The second ratio is the outer diameter ratio the thickness of the pressure vessel here. All this ratio calculated based on the assumed thickness. Once you already calculate these two ratio, what you need to do is you need to determine factor A. What is factor A? Factor A can be obtained from figure 8.10. Where is figure 8.10? This one, figure 8.10. Okay, this one is actually taken from the reference book. You see, here is the ratio, here is the ratio. And based on these two ratio, you can actually determine our factor A on the horizontal axis here. Okay? So this one will be provided during final exam if let's say you want to use the chart or graph here to determine the factor A. Okay? Once you already determine the factor A, right? Now you need to proceed to figure 8.11 to determine our factor B. Where is graph of figure 8.11? This one. The graph here will also be provided. Just now we already determined the factor A, right? Just now we already determined the factor A from our figure 8.10, right? Then now we proceed to use the factor A and also the operating temperature in order to determine our factor B here. Okay? So this is how we determine our factor B under the step here. Okay, look at here. Depends on the factor A, depends on the value A that you obtain from the graph here. If let's say later the value of the factor A that you obtain from the figure 8.10 here, the value of the factor A here is actually fall within the left hand side of figure 8.11 here. Then you need to proceed to calculate the allowable external pressure by using the equation here. Okay, let me repeat. If let's say later the value of the factor A that you obtain from figure 8.10 here is actually too small, and some more the value is too small, and some more the value is actually fall within the left hand side of the graph here. Because on the left hand side of the graph here you don't have any line, so in that case you cannot read the factor B on your right hand side here. So if let's say the value of the factor A is off scale to the left of figure 8.11. Off scale to the left, that means fall on the left hand side of the line here. We call it off scale. If let's say the value of factor A is somewhere here, and somewhere here we don't have any line or curve to read the factor B, then in that case we directly proceed to calculate the allowable external pressure by using the equation here, directly by using the A value that we determine from the figure 8.10 here. The pressure here we calculate by using equation here is known as allowable external pressure. Unit PSI. And the value here, the pressure here is actually the maximum external pressure that can be withstand or supported by your pressure vessel. Okay? So in other words, if let's say now the external pressure that you are going to withstand is actually smaller than the maximum pressure that can be withstand by your pressure vessel, then in that case means that the thickness of the pressure vessel that you assumed just now is actually suitable, thick enough to make sure it can be safely operated. Okay, this is the meaning of P here. We call it allowable external pressure. Okay. So in order to utilize the equation here, we also have to know what is the modulus elasticity, okay, of the material, okay, that we are going to use to fabricate the pressure vessel. Okay, this one, okay, you try to include the unit that we are going to put it is PSI. Okay, this one you download the lecture notes, then you try to include the unit. I forgot to include the unit. Okay, the modulus of the elasticity that you are going to dump into this equation must be measured in unit PSI. Okay, then this one is T. The T here is the thickness of the pressure vessel that you assumed just now. And this one is actually the outer diameter of the pressure vessel. Okay, so if let's say a value here is bigger or equal than the external pressure that you are going to withstand, then means that the thickness that you assumed just now is actually thick enough. Okay, if not, then you need to try to assume a new thickness and try to repeat the calculation, the procedure, the step that I explained just now. Okay, so beside that, okay, so we continue. Okay, this one, we only apply this equation if let's say we cannot get the factor B from figure 8.11. But if let's say now the factor A is actually fall on the right hand side of the graph 8.11 here. Right hand side, that means somewhere here. And somewhere when, let's say the A value is here, and somewhere when you draw out the line, you can touch the line, touch the curve here. Okay, but of course you also need to decide what is the operating temperature that you are going to use. If let's say you are going to use the temperature here, then you touch the curve here, then you draw a horizontal line in order to get the factor B from the right hand side of the figure here. Once you have the factor B, then what we need to do is we proceed to apply the equation in step number 6 here in order to calculate the allowable external pressure. Then we put in the factor B, okay, similar outer diameter and thickness. Then we calculate the maximum or allowable external pressure, okay, of your pressure vessel. If let's say bigger or equal to the external pressure that you are going to withstand, then yes, the thickness here can be accepted. Okay, remember, if let's say factor B cannot be obtained, then first equation here. If factor B can be determined, identified, then we select the second equation here. All these equations will be provided during the final exam. If let's say you want to apply this equation, and for sure, of course, you have to know what is the meaning of the symbol here, and also the unit of the value that you are going to put into the equation in order to get the correct unit with the correct answer. Okay, this is how we try to determine the thickness for our pressure vessel. Okay, so far any question with the step that I explained just now here before we proceed to the stiffener? This one is the method how we determine a thickness without using the stiffening ring. But if let's say now you want to try to install the stiffener or stiffening ring, okay, you want to install the ring, then you want to know, after I install the stiffener ring, after I install the stiffener, then what is the thickness of the pressure vessel that I need to try to fabricate for my pressure vessel? Then you need to follow the step that I'm going to explain. Okay, first, okay, you imagine this one is your horizontal, let's say this one is your horizontal cylindrical pressure vessel. This one is your ring. Now you have two rings here. If let's say you measure from the center of the first ring until the center of the second ring here, the gap here is known as the interval of our stiffener. Normally is represented by using LS. Okay, so if let's say the interval of the stiffener is not provided in the question and you want to calculate, then this is the equation we apply. Outer diameter, thickness, outer diameter, and this is the equation. Okay. Then of course, what is our thickness? Thickness, we need to try to come up with an assumption. We need to assume a thickness for the calculation here. Okay, because we don't know what is the thickness, and we want to try to calculate and try to check again later. Okay, so meaning that we are going to apply the try and error method to determine the thickness. Okay, and also you need to know what is the cross section area of the ring here. Okay, and the unit is measured in inch per second. Inch square. Okay, inch power of 2. Okay, inch power of 2. Inch normally represented by using double prime. Feet, 1 dot. Okay, okay. So once you already identify the interval of the ring and also the cross-section area of the ring, then what you can do is you try to calculate factor B by using the equation here. DO, outer diameter, millimeter. T is the assumed thickness. PE, be careful, external pressure that you want to withstand. AS, cross-section area of the ring. LS, internal between the ring. Then you will get the factor B. Okay, once you already calculated the factor B, directly go to figure 8.11. This one, based on the calculated factor B, let's say the calculated factor B is 5,000 here. Then here you draw a horizontal line. And someone, let's say now the operating pressure is, let's say 900. Then we touch the line here. Then we go down. Then we try to get our factor A from the graph here. Okay. Once you already identify the factor A, then you proceed to apply the equation here to determine the moment of inertia by using the equation here. Moment of inertia, IS. DO, outer diameter, millimeter. LS, interval of the ring, inch. T, assumed thickness. AS, cross section of our ring. LS, interval of the ring. Be careful. A here, factor A. Identified based on step number 4 here. Then divided by 14. Then to see what is the moment of inertia for the pressure vessel here. What is moment of inertia? The moment of inertia is actually one of the properties of our pressure vessel here. But in this case, we are not going to discuss and expand what are to discuss in detail or expand the background of the moment of inertia. Okay, why? Because if let's say we try to discuss what is the moment of inertia, it will become more on mechanical engineering. But if let's say you want to know what is the moment of inertia, you can try to go after this. Okay, but at least at this stage, you know what we are going to calculate. IS is known as the moment of inertia. Okay, and normally at the same time, okay, the moment of inertia of the stiffening ring will also be provided in the question. Then in this case, you need to try to do a comparison. You need to try to compare the moment of the inertia that you calculated just now, compare with the one that given in the question. Okay, if let's say now the IS, now the moment of inertia you calculated is smaller than the I that given in the question, means that the thickness that you assumed just now is actually suitable and thick enough in order to withstand the external support if let's say you try to install the stiffening ring on the outer surface. This is how we try to determine the thickness of the pressure vessel if let's say we want to install the stiffening ring. Okay, any question with the procedure here before we proceed? Okay, I assume no question. Okay, then now we proceed. Okay, now we look at this example. Okay, I give you 1 minute to try to read the example here. Okay, so now we go to example 1. Okay, so look at here. Now I will try to show you an example how to apply the step and equation that I tried to explain just now. Okay, so now a tower. Okay, tower you assume is a cylindrical tower. Normally the shape of the tower that we are going to construct is cylindrical. Okay, some more is tower that means the vertical one. Okay, now the what we call the inner diameter of the tower here is 4.5 meter, and some more the tangent to tangent length. Tangent to tangent length, that means tangent here until here. This one is the height or the length they given. This is what we call tangent to tangent length, 8 meter. Okay, so it's operated under vacuum. Vacuum, that means lower than 1 atm. And some more, the operating temperature is 700 Kelvin. Okay, tower shell that means the outer surface here is constructed from carbon steel plate. And some more, the modulus of elasticity E is this one, measured in PSI. Okay, so part A, determine the shell thickness without stiffness. Now they ask you, what is the thickness of the shell here if let's say I'm not going to install any stiffening ring or stiffener? Okay, so first you have to identify this one is internal or external pressure. Common sense, environment outside the pressure vessel must be 1 atm. If vacuum, I told you already, that means the operating pressure is lower than 1 atm. So means that now the pressure outside the pressure vessel is stronger than the inside one. So in this case, we need to consider external pressure calculation. Okay. Okay, so now since we know this one is external pressure, okay, some more we just want to increase the thickness without using any ring. So what we can do is we can refer to the step that I try to list out here in order to calculate the thickness. Okay, remember this one is when we try to install the ring. Okay, so first, okay, we need to assume a thickness. Okay, in this case, we assume 0.5 inch. Double prime, that means inch. Okay, we assume 0.5 inch. Okay, so inch, first we convert it to become millimeter. So if let's say you want to convert the unit, the conversion factor will be provided. Okay, if let's say in final exam you need a conversion factor, then of course it will be provided. Now we convert the assumed thickness from inch to become millimeter. But this millimeter, the thickness here, actually we already include the corrosion allowance, 2 millimeter. So that's why if let's say we want to try to exclude, okay, the corrosion allowance, we need to use 12.7 millimeter minus 2. Then this one is actually the real thickness that actually we are going to use for our calculation. This is the thickness for the shell without including the corrosion allowance. Okay. Okay, so now, given that the inner diameter is 4.5 meter, if I'm not mistaken, 4.5 meter, convert it to become millimeter, 4,500. This one is common sense. Meter convert to millimeter, this one common sense you have to know. Even though conversion factor is not provided, but this one common sense you have to know. Inner diameter, add out with the thickness. Thickness you have to consider the left hand side and right hand side thickness. Okay, because this one is a pressure vessel, thickness here and thickness here, so that's why we use the thickness multiply with 2. Then this one is the outer diameter. Okay, first we need to calculate the ratio. What is the ratio? Outer diameter divide the assumed thickness 10.7. This one is the first ratio. Second ratio, length given 8,000 millimeter divided by the outer diameter, this one, then you will get the second ratio. And some more, the operating temperature is 700 Kelvin. 700 Kelvin convert to Fahrenheit, 800 Fahrenheit. 800 Fahrenheit. Okay, 800 Fahrenheit. So this one is the operating temperature. Then you use the operating temperature ratio here. Then next you proceed to figure 8.10 in order to determine the factor A value. Okay, so you see first DO over T. What is the value? 422.5. 422.5, that means somewhere between the line here and also the line here. That means somewhere between here lah. Am I right? The gap here. But never mind, we proceed to a second ratio. 1.77. L over D naught. Okay, 1.77. Somewhere here. Between 1.8 and 2.0. Okay, look at here. 1.77, somewhere between 1.8 and 2.0. What you need to do is, you need to interpolate the gap here to see where is your 1.77. Then after that, you draw a horizontal line. Okay, you draw a horizontal line. Then here is 1.77. You draw the horizontal line until you cut the two curve that we already identified just now, this one and this one. Okay, so now we know 422.5 is somewhere between the line here and line here, between here. Then based on the horizontal here, based on the horizontal line here, you try to interpolate again to see where is your 422.5. After you interpolate, you know, oh, 422.5 is somewhere here. Then at the intersection point here, you draw a vertical line down. Then you can get the factor A here. Okay, you can get the factor A here. And the factor A, you need to be careful. This one is 0.0001. Yeah, this one is 0.0001. Here is 0.00001. Here is almost, let's say, a 9. Meaning that here is actually 0.00009. So this is the value of our factor A. Okay, so remember, interpolate here, draw a horizontal line, and then based on the gap, based on the two curves that we already identified, we interpolate again to see where is our ratio. Okay, then only we go down to get the factor A here. This is not that simple. You need to make sure you know how to interpolate. Okay, this is the factor A. Okay, so now we go to figure 8.11. 0.00009. Where is the value? Oh my god, somewhere here on the left hand side. So means that based on the value of the factor A we identified just now, we don't have any line here. So in that case, remember I told you already, if let's say the value of factor A is too small, okay, and we cannot identify the factor B, then we proceed to directly to apply the equation here. So you see, immediately I apply the equation here. A is the value of factor A. This one is the modulus of elasticity. Outer diameter, okay, outer diameter divided by thickness, the ratio here. You just put in the value here, the ratio. And then you press your calculator. This is the maximum pressure that actually can withstand by your pressure vessel. What is the external pressure? External pressure is 1 atm. 1 atm equivalent to 14.7 psi. Because based on the equation here, the unit of the pressure is psi. So if let's say you compare, you see the pressure that actually can be withstand by your pressure vessel is smaller than 1 atm, smaller. So that means the assumed thickness here cannot be accepted. So in that case, what we need to do is we need to further increase the thickness, okay, and repeat the calculation here again. Okay, okay. So now very simple. Okay, just now we assume 0.5 inch. 0.5 inch convert to become millimeter, become 12.7. Am I right? Okay, 12.7. This is the first assumed thickness, but it is rejected, cannot be accepted. Now we want to try to further increase or decrease the thickness. Common sense, increase the thickness, okay, to make sure it's strong enough. How to increase? Okay, you use the 12.7 millimeter here divided by 2. Press your calculator, divided by 2, what is the value? 6.35. Then after that, you use the value here, add up with the value 6.35. What is the value? What is the answer? Add up. 19.05 millimeter. This is the second assumed thickness that we are going to use, okay, in order to check whether it is strong enough to withstand the external support or not. So meaning that the first thickness we just simply assume. If let's say it cannot be accepted, then we try again by using the second assumed value. How to get the second assumed value? Use the first assumed thickness, okay, divided by 2, then add up with the first assumed thickness, then we will get the value here. This is the second assumed thickness that I'm going to use. Okay, similar, minus the corrosion allowance, we will get the thickness, okay, the real thickness. And then you want to calculate the outer diameter, similar, this one multiply with 2, add up with the inner diameter, we get the value here. Similar, we calculate the ratio here and also the ratio here. And based on these two ratios, you go to figure 8.10 to determine your factor A. Okay. L over D naught 1.76, somewhere between 1.8 and 2. So you interpolate to see where is your 1.76. Then you draw a horizontal line. Okay, 1.76 between 1.6 and 1.8. So you need to interpolate here lah, to see where is the 1.76. And then you draw a horizontal line. D naught over T, 266. Where is 266? Between 250, the curve here, and also 300. So that means between the point here and also the point here. So from the horizontal line here, you try to interpolate again to see where is your 266. Once you already identify the location of 266, then you proceed to try to draw a vertical line down to get your factor A here. Okay, so in this case, I know my factor A is 1.8 multiplied with 10 power of negative 4. And some more, I proceed to a figure 8.11, you see 1.8 10 power of negative 4 is somewhere here on the right hand side of the graph here. So meaning that I can proceed based on the factor A that I already identified, I go up. And some more, just now my operating temperature is 800 Fahrenheit. So I am going to refer to the second curve here. Touch the curve, draw a horizontal line to the right hand side, interpolate, you will get the value of factor B. So once you get the value of factor B, you proceed to apply the second equation, put in the value of factor B, then you try to check what is the maximum SR pressure that can be withstood by your pressure vessel. And some more, the value here is still lower than 15 psi, that means that the second assumed thickness still cannot be accepted because it is not strong enough. Okay? Okay, so remember, if let's say the factor B can be identified from figure 8.11, then you can just proceed to apply the second equation here. So similar, the second value still cannot be accepted because not strong enough. Then what we are going to do is we use a second assumed value here, proceed to add up with 6.35 millimeter again, then you will get the third assumed thickness. Now our third assumed thickness is this one, 25.4 millimeter. Similar, minus the corrosion allowance, get the thickness, multiply with 2, add up with the inner diameter to get the outer diameter. Similar, we proceed to identify the ratio here, then refer to figure 8.10 to get the value for factor A. Once you get the factor A, because of factor A is fall on the right hand side of figure 8.11, then you can actually identify the value for factor B. Then you proceed to continue with the second equation to dump in the value of factor B to determine the maximum pressure that can be withstood by the pressure vessel. And now this time, the maximum pressure that can be withstood by the pressure vessel is bigger than 1 atm. So meaning that if let's say the thickness here is utilized, it is actually strong enough to try to withstand the external pressure that given in this question. Okay, so this the thickness here can be accepted, but you see the external pressure that you want to support is 14.7 only. But if let's say you install the thickness here, the maximum external pressure can be withstood is actually 21.96. So meaning that if let's say you want to try to reduce the cost, you want to try to reduce the thickness, can. So meaning that you can try to adjust again to reduce the thickness to make sure the thickness is actually strong enough. Okay, and the suitable thickness can be actually be selected between 25.4 millimeter and 19.05 millimeter here. Okay, but you need to make sure that it's bigger than 14.7. Okay, so means that if let's say you want to reduce the cost, why? Because the external pressure that you want to support is only 14.7, but this one can up to 21.96, and you want to reduce the thickness. Okay, in order to reduce the cost, can. Maybe you can slightly adjust the thickness here to slightly reduce the thickness. Okay, as long as it's higher than 14.7, then it can be accepted. Okay, so now at least now you have a range, you know. Okay, then later you can try to adjust accordingly lah, if let's say you want to reduce the cost, okay, of fabrication. Okay, this is how we determine the thickness for our pressure vessel. Okay, so far any question before we proceed to part B? The method is almost similar lah to I explained just now. Okay, so far any question before we proceed to part B? Oh, one more thing. Okay, tomorrow we have tutorial, and our tutorial will be conducted as usual tomorrow. Tomorrow for our tutorial will be conducted in our campus. Then we refer to the classroom that assigned by the university, because I'm not sure, okay, how is our computer lab now. Okay, if let's say the aircon is still got problem, then okay, but this one I'm not sure. Okay, then we just refer to the classroom that are assigned by the university lah. Tomorrow we just refer to a timetable, then we go to a new classroom that is assigned by them. Then tomorrow our tutorial class will be conducted as usual. Okay, so now we go to part B. Just now we only increase the thickness to withstand the external pressure. But now part B is a bit different. Determine the thickness of the shaft if the stiffener is installed on the outer surface, and some more are located with 0.5 equal spacing. So means that this one is actually the interval, the spacing between the ring LS, 0.5 meter. And some more, the material that we use to fabricate the stiffener is carbon steel plate, and the thickness of the stiffener is 8 millimeter. The cross-sectional area of the stiffening ring is this one. This one is AS. And the I, the moment of inertia of the stiffeners, is this one. Okay, so now, okay, they want to try to reinforce the pressure vessel by using the stiffeners. If let's say we reinforce the pressure vessel here by using stiffeners, they are asking you what is the thickness of the thickness. Okay, what is the thickness of the pressure vessel here that we need to fabricate? Okay, first, you need to refer to the method that I introduced to you just now here. This one. This one. Okay. This one, we can only apply the equation here if let's say we try to reinforce the outer surface by using the stiffening ring. Okay, now the LS is provided, then this one don't need, okay, because LS is now already provided. Then we can proceed to this one. Calculate B and then calculate our IS. Okay, so now we need to proceed to calculate our factor B. Okay, similar, before we proceed to calculate our factor B, we need to assume a thickness. Okay, try and error. Similar, we assume 0.5 inch for the thickness of our shell. Convert become meter, minus corrosion allowance, 10.7 millimeter. This is the real thickness without corrosion allowance. Thickness multiplied with 2, add out with the inner diameter, then we will get the outer diameter of our tower. And then we plug in the outer diameter, external pressure that we are going to withstand, 14.7, thickness, 10.7 millimeter, cross section of the ring, this one, spacing or interval between the ring, this one. But this one you need to convert become millimeter lah. Okay, become 500 milliliter. Then you will get the B factor. And the unit of B factor is PSI. And then now, based on the calculated B factor, we go to graph figure 8.11. Okay, here is the calculated value B. Then here we draw a horizontal line until it touches the operating temperature 800 graph here. And then we go down, interpolate, then we will get the value for our factor A. Interpolate, the value of our factor A is 2.9 multiplied with 10 power of -4. Then proceed, you apply the equation here, put in the A value into the equation here, outer diameter, interval of the ring, assume thickness, cross section of the ring, internal of the ring, and the A value, factor of A. Then you press your calculator, then this is the moment of inertia. The unit of inertia is millimeter power of 4. Convert to become cm power of 4, this is the value. Then now you compare the value here with the moment of inertia of the ring that given here. If let's say the calculated IS here, the moment of inertia of the shell that calculated is smaller than the maximum value that can be supported by the ring here, meaning that the assumed thickness here is actually acceptable. And later, if let's say the shell, the thickness of the shell is fabricated by using the value here, it can be safely operated. So the thickness here can be accepted. And this is the thickness that actually we can consider if let's say we want to try to install the stiffeners. You see, by using a stiffener, just now the thickness is almost 25.4 millimeter. But now this one only 10.7 millimeter. Okay. Okay, this is how we determine the thickness. Okay, if let's say we want to install the stiffening ring. Okay, so far any question before we proceed to the last part of our today lecture? Okay, so far in our previous lecture and also our lecture just now, we only consider the internal pressure and external pressure for our pressure vessel. But common sense, okay, if let's say we want to ensure the pressure vessel can be safely operated, not only the internal and external strength, there are also a lot of other stress, okay, we need to consider. For example, if let's say later you fill in the pressure vessel here by using your processed liquid, okay, or gas liquid mixture, then you need to make sure the strength or the pressure vessel here is actually strong enough in order to support the stress, okay, that contributed by the weight of the liquid or the processed fluid that you are going to handle by using the pressure vessel also, okay. So and also sometimes if let's say you are going to install the pressure vessel, let's say outdoor, then in that case you also need to consider the load we call wind load. Meaning that when the wind come from here, let's say come from here, okay, it can be considered as a type of the stress that can be found on the surface of your pressure vessel here. So in that case, you also need to make sure the pressure vessel that you are going to fabricate is actually strong enough in order to withstand the stress that actually contributed or exerted by the wind load here. Okay, all these stresses, okay, are considered under the combined loading, and this is also the meaning of our combined loading. Okay, so meaning that we will also consider the other loads that we are going to we are also consider the other loads that is going to be experienced, okay, by the pressure vessel here to make sure the strength, okay, of the pressure vessel here is actually strong enough in order to withstand all these, okay, other stresses. This is what we call combined loading. Okay, so as I told you just now, there are a lot of other stresses we need to consider in order to make sure our pressure vessel can be safely operated. Okay, the first one is the pressure. This one should be no problem because our thickness is actually calculated based on the internal or external pressure. Okay, but actually when we try to analyze, okay, all the stresses that can be found in the pressure here, right, actually they can be further divided into circumferential stress and also the longitudinal stress. Okay, so if let's say now you want to try to calculate the circumference stress, this one, circumference stress, this one, then you can apply the equation here. If let's say you want to calculate the longitudinal stress due to the pressure, the vertical one, then you can apply the equation here. And this one, the equation here are actually similar to what we learned in our previous lecture. Okay, just we try to recap and recall again. And don't forget, these two stresses, they are actually contributed due to the pressure, okay, of the pressure vessel. Okay, beside that, as I told you just now, okay, if let's say you try to transfer your process content, the content of process fluid inside the pressure vessel, okay, you need to consider the weight, okay, that going to be supported by the pressure vessel here as well. Okay, and when you try to transfer in the mixture of content, okay, the weight, you will also contribute another type of stress which is known as direct stress. And the direct stress can be calculated by using the equation here. Okay, okay, inner diameter, thickness. The W here is known as dead weight load. This one can be calculated by using the equation that I'm going to show you later. Okay, and the direct stress here can be positive or negative value. If let's say it is the direct stress here, okay, the direct stress here is considered as a tensile stress, then it is a positive value. If the direct stress here is a compressive stress, then it's a negative value. Okay, so let's say now we have a pressure vessel here, and now we try to support our pressure vessel. Let's say we put a support here to hold our pressure vessel. If let's say the pressure vessel is supported by using the support here, right? Okay, normally the part, okay, above the support is considered as negative. Why? Because the direct stress that can be found above the support here is normally considered as our compressive stress. For the stress, direct stress that can be found below the supported here is normally a positive value. Why? Because normally the direct stress that can be found below the supported here is actually treated or considered as a tensile stress. Okay? This is how we try to put the positive and negative sign for our direct stress. Okay? Based on either is considered as a tensile or compressive stress. Tensile, positive. Compressive, negative. Okay? Okay, beside that, okay, when we install the pressure vessel, we also need to consider the bending stress. Bending stress can be calculated by using the equation here. Okay, the bending stress can be compressive or tensile. Okay, and it can be calculated bending stress by using the equation here. And the M represent the total bending moment. Okay, and the IV represent the second moment of area of the vessel, and the IV can be calculated by using the equation here. Okay, so the equation here will be provided if let's say you want to calculate the bending stress and also the second moment of area of the vessel. Okay, so beside that, okay, in the pressure vessel, you also need to consider the torsional shear stress. And the torsional shear stress can be calculated by using the equation here. Okay, T is the applied torque, okay, and IP is the polar second moment of area. Torsional shear stress can be calculated by using the equation here. But normally the torsional shear stress is actually very small, the stress, and normally it can be omitted or not in our calculation. Okay, but if let's say you still want to calculate the torsional shear stress, then you can proceed to apply the equation here. Okay. Okay, so now here are all the equation. Okay, here are all the equation that I showed you just now. Okay, to calculate the longitudinal and circumferential stress, this one and this one. Direct stress due to the weight or the mass of the process fluid, this one. Bending stress, okay, this one. How to calculate the IV? By using the equation here. Torsional can be ignored, so that's why it's not included in the table here. Okay, and when you add out this one together with the direct stress, okay, and also a bending stress, when you add up these three values together, then the total answer is known as total longitudinal stress. Okay, and what is the function of our total longitudinal stress? Okay, I will try to explain by using the question tomorrow during our tutorial section. And actually, total longitudinal stress, this is actually one of the parameter or variable, not parameter, the criteria, one of the criteria that actually can allow us to try to check, okay, whether the tower, the design of our tower is actually stable or not. Okay, so based on the total longitudinal stress here, it allows us to identify whether the design of our tower is actually stable or not. Okay, How to calculate the total longitudinal stress? By add up the value here, here, and here together. Okay. So later, this one I will try to discuss in further detail by using the question in our tomorrow tutorial. Okay. So if let's say you want to check, okay, whether the column or the tower, okay, is actually stable or not, okay, can be safely operated or not, okay, then we can also calculate the value here. Okay, we call the critical buckling stress. Okay, critical buckling stress by using the equation here. Okay, this is also one of the criteria that allow us to try to evaluate whether the tower or the column that we are going to construct is actually stable or not. Okay, can it be safely operated, okay, without buckling, or not? Okay, this is one of the criteria, and this is the equation that we can apply. And actually, this equation is actually derived based on the original equation here. But common sense, because normally we will try to fabricate the pressure vessel or our equipment by using the stainless steel or steel. Why? Because steel is normally, it can, compared to metal, okay, the steel is actually the corrosion resistance is much stronger. So that's why normally we are trying to fabricate our equipment or tower or pressure vessel by using steel. So that's why the scientists and engineer, they already try to modify the equation here. They put in the modulus of elasticity of steel into this equation. And then some more, they try to include the suitable factor of safety into this equation. And then they try to derive the critical buckling stress for steel, okay, for our calculation. So it means that if let's say our equipment and pressure vessel, they are fabricated by using steel, then we can directly to use the equation that given here. If let's say your equipment or your pressure vessel, they are not fabricated by using steel, then in that case, sorry, you cannot proceed by using the equation here. You need to start with the original equation here. This one is the common equation that can be used for any material. But of course, if let's say you are using different material, then you need to put in what is the elasticity of the material that you are going to use. Okay, remember the equation here. You are only allowed, okay, you are be allowed to use the equation here if let's say the equipment is fabricated by using steel. Okay. So beside that, okay, here are all the stresses that actually we need to try to consider, okay, in the pressure vessel. So beside that, okay, if let's say now you want to estimate the weight of the pressure vessel, okay, then okay, we can try to calculate or estimate based on the equation of that weight. Okay, what is the equation that actually we can calculate the dead weight? This one, the equation here. Okay, and all the variable you can consider the definition and also the constant that given here. So later tomorrow in our tutorial question, okay, I will try to explain in further detail how to apply the equation here. But at this stage, you have to know this one we call dead weight load. Means that we are going to use the equation here to estimate the weight of our pressure vessel. Okay. So beside that, okay. As I told just now, we need to consider the wind load. Why? Because okay, the wind load, okay, can also be considered as one of the stresses that actually we need to consider, okay, in order to make sure our pressure vessel is actually stable, especially you are going to construct the pressure vessel outdoor. How to determine the wind load? Okay, by using the equation here, this one. Okay, X is actually the height of the column or the tower. W, how to calculate? By using the equation here. okay, wind pressure multiplied with the total diameter of the tower or column that you are going to evaluate. What is wind pressure? The wind pressure is normally assumed this one, 1280, meaning that this is a constant that we always use, okay, for our wind pressure here in order to calculate our W. Then this one is the one of the equation that we can utilize to calculate the wind load in order to evaluate the stability of our column. Okay, so okay, okay. So for this one, okay, the wind load, okay, this one I will explain by using our tomorrow tutorial question. Okay, so this one I will explain by using our tutorial question tomorrow. Okay, okay. So far we only cover the wind load, depth weight load, and also the different stresses that can be found on the surface of our pressure vessel. So if let's say you are going to install your equipment in the region that you need to consider the earthquake, okay, then you also need to consider the stress that exerted by the earthquake. And the relevant equation, you can refer to your reference book in order to get the relevant equation. Okay, if let's say you want to try to consider the stress that exerted by the earthquake. Okay, but for our lecture, we are not going to cover the earthquake. But if let's say you want to get the relevant equation, then you can try to get it from the reference book. Okay, so far this is our lecture 7 today. Okay, so far any question regarding to our lecture before we end our lecture today? Okay, so far in our today lecture, I try to cover the calculation, how to determine the thickness for the pressure vessel to withstand the external pressure. For the combined loading, I just quickly try to explain and try to introduce the relevant equation to you. But I will try to explain more how to apply the equation here, okay, to solve the question, to check the stability of the pressure vessel or tower by using the question that we are going to discuss in our tomorrow tutorial section. Okay, for combined loading, at least you know, okay, what are the equations we are going to use, okay, and what are these equations, okay. Okay, so far any question? Okay, if let's say no question